So X-ray crystallography is a technique that we use to figure out how the atoms are arranged. What have we figured out? Well, there are several different common ways that atoms are arranged. Crystalline lattice is what we use, the term we use to refer to how the atoms are arranged. It's a regular arrangement in a crystalline solid. It goes in all three dimensions. And the way the particles arrange themselves is governed by energy. They're going to arrange themselves in a way that minimizes their energy. So in looking at these crystalline structures, we frequently look at a unit cell. And a unit cell is the smallest unit of a crystal that when you repeat it in 3 dimensions gives the entire crystal lattice. So this pink box here, if I take that pattern and repeat it over and over and over, I'll get the crystalline lattice. We use circles to represent the lattice points. That's an atom, an ion, or a molecule. That's the center of one of those. This dark square here indicates the unit cell. So we're looking for the smallest piece that we can copy over and over again. It's a little bit like putting, tiles together on a bathroom floor or something. So there are different kinds of unit cells. Cubic unit cells have sides that are all equal in length. So a cube has equal length edges, equal edge lengths, and 90-degree angles. So it has a cube shape, right? So here's a cube, all the sides are the same length and the angles are 90 degrees. Then there are variations of this. There's a tetragonal, so it's a tetragon, but now the angles on the bottom, the base, and the top are not 90 degrees. You can have orthorhombic, so here we have all of the angles being 90 degrees, but the lengths of the edges aren't all the same. There's rhombohedral, so now all the angles are kind of wonky. Hexagonal, monoclinic, triclinic. So there are all these names, okay? And the names just describe what's going on with the angles. Good news is you don't have to learn all these names, right? Yay! We are only going to look at some of the unit cells. What we're going to do is we're going to look at unit cells where each atom is the same as the other atoms in that structure. So when we're looking at these cells, we're going to have pictures where the circles are different colors. That doesn't mean they're different atoms. We're just looking at all the lattice points being the same atom or molecule. The colors are just to help us see what's going on, because that can be a little challenging. So some numbers that we associate with unit cells. Coordination number, how many atoms that each atom is in direct contact with. So one of the things that lowers the energy for a crystal is that the intermolecular forces are strong between neighboring crystals, right? So you get strong intermolecular forces due to nearness, and that lowers the energy. So if an atom is in contact with a lot of different atoms, it's going to have a lowered energy because it has all these interactions, compared to if it was only interacting with 2 or 3 atoms, then it would have higher energy. So coordination number gives us an indication of what's going on in this unit cell. And the other number we look at is packing efficiency. So this is the percentage of the volume of the unit cell that's occupied by the spheres, the atoms. If you have a high coordination number, you tend to have a greater packing efficiency. Any of you worked in a packing house? Yay, one person. In Reedley, most of the people your age have worked in a packing house at some point. So this fruit comes in, and fruit is generally spherical, right? And it gets put into boxes after this other processes happen. We're just going to look at the boxing of the fruit. When you put the fruit in the box, can the box be 100% full of fruit without any airspace? No, because round things don't pack together so well, right? If they were cubes, you could completely fill it up if the box was the right dimensions. But they're spheres, and so there's going to be some gaps between the fruit. Higher packing efficiency means less empty space in the box of fruit. Okay? So less empty space in the unit cell, that the atoms are packed more closely together.
Would that make the crystal stronger?
Would that make the crystal stronger? Probably. Probably. So these are three different types of cubic unit cells. So the angles are right angles, and the lengths of the sides are all equal. So this is a simple cubic where you just have things stacked on top of each other and next to each other. This is a body-centered cubic where you've got those four, but now you've also got one stuck in between, and then the face-centered cubic. Here we've got a yellow one and purple ones. This yellow one is the same kind of atom or molecule as the purple ones. We just made it a different color to make it easier to look at. And then this table is giving us the coordination number, packing efficiency, and also the edge length in terms of the radius of the sphere. This is a summary, and then we're going to look at each of these individually. So the simple cubic unit cell. We've got one atom at each corner of a cube. So that involves 6 atoms, right? 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms. But if you connect the centers of those atoms, and that is the unit cell, it does not contain 8 atoms, right? Because it's only part of each of these atoms. It's 1/8 of each atom. So in this cubic unit cell, you have 1/8 of 8 atoms, so you have 1 atom in the unit cell. The atoms touch along their edges. So between this atom and this atom, they're actually touching each other here and here and here. And so we can calculate the length of the edge in terms of the radius of the particle, the atom or molecule. So if this atom has a radius of r, then the length of the edge must be 2r, because it's 2 radii in length. Does that make sense? So here is that cubic unit cell. We've kind of pulled the atoms apart to make it a little easier to look at. This is what they would really look like. They are touching on the corners. But now we want to focus on this atom in the corner. The coordination number is how many other atoms is that one touching. So it's going to touch this one, and this one, and this one, and that one, and one over here, and one up there. It has a coordination number of 6. It's in edge contact with 6 other atoms. The packing efficiency here is 52%. 52% of the volume of this cubic unit cell is occupied by atom, which means that 48% of it is empty space. Any questions? Got some skeptical looks. So here we're going to look at a 2-dimensional lattice. This is easier to look at. So thinking just 2 dimensions, you can think of this as pieces of fruit or marbles or tennis balls or whatever you want. You're sticking them in a box and you're lining them up like this. This is asking us to calculate the packing efficiency. So the packing efficiency is in 3 dimensions. It's the volume occupied by the things divided by the total volume of the cubic unit cell. In 2 dimensions, it's area instead of volume. So the unit cell here is from the center of 1 over here, like this. So this white square. If we take that pattern and repeat it over and over and over again, we get the entire pattern. So the packing efficiency, I don't want to use red, it doesn't look good with the purple. So packing efficiency, there should be an abbreviation for that. I'm going to call it PE, packing efficiency. That's the area of the atoms divided by the area of the cell times 100. Like all other percentages, it's the part that you're interested divided by the whole thing. So we're interested in this unit cell, this little white square. So if we call the radius R, so this part is R, what is the area of that sphere? I'm sorry, the square. What's the area of that white square?
4r squared.
Yeah, 4r squared. Because each side, let's draw it down here. Each side is 2r. Right, we can see that there's 1r and then another 2r on each side. And so area equals 2r times 2r. So the area of the unit cell is 4r squared. What's the area occupied by the purple circles? Well, this is 1/4 of a circle, right? And that's 1/4 of a circle. We have 4 quarters, so that equals 1 circle, right? So what's the area of one of those circles? What's the area of a circle? Area equals pi r squared. Pi r squared. So the area of the atoms, there's 1 atom in that square. The area of the atoms is pi r squared times 100. The r squareds cancel out. So it's pi over 4 times 100. But we like actual numbers. Do not use 3.14 for pi. Your calculator has a pi button. Use it. So pi divided by 4 times 100. My calculator's messing with me. I hate it when it does this. It's giving me 25 pi. That's not... I'm going to pause. Okay, I had a discussion with my calculator and we got it straightened out here. 78 point, I'll call it 54%. Now, in terms of significant figures, you could actually go on and on and on because 4 is an exact number. And pi, if you're using the pi button on your calculator, is probably at least 9 digits, if not more. Do we really care what the rest of those digits are? Not really, no. Any questions? Body-centered cubic. So here we have an atom in the middle and 8 atoms around it. So this yellow one is completely inside of the unit cell. And again, we have 1/8 of an atom on each corner. Now, when we're trying to find out the length of the side, L, it's a little more complicated because it's R, it's 2R, but then there's a little bit extra in there because of that gap. So we have right angles here, and so you can look at this in terms of the Pythagorean theorem that c squared from diagonal corner to diagonal corner equals b squared, the diagonal on one side, plus l squared. The reason we're using c here is because c is a line that's going through this atom, this purple atom, which is directly touching the yellow one, directly touching the purple one. So we can get c in terms of r's, because there's one r for this purple one, two r going through the yellow, and another r for the purple. So c is equal to 4r. And so then we can plug those things in there and solve it, and we end up with the length of the side is 4r over the square root of 3. That's just so lovely, right? But we can't really simplify that anymore. It is what it is. So here's looking, this is the picture we looked at earlier. We have one atom in the middle, 1/8 of each atom's on the corners, and so this unit cell has two, the equivalent of 2 full atoms inside of it. This is what the unit cell looks like when you have the full atoms on each corner. And here we're looking at adjacent unit cells to figure out what the coordination number is. How many other atoms is this purple atom touching directly? And the coordination number is 8. So this is a higher coordination number. The packing efficiency is going to be greater. It's 68% instead of, what was the other one, 52%? So this is more efficient packing. There's less empty space. And we can do problems like this. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Well, we're going to need this guy right here. Man, my pointer's jacked up today. L equals 4r over the square root of 3. So I'm going to write that down before I forget. L equals 4r over the square root of 3. So our unit cell is a cube. What is the volume in terms of an equation of this cell? This side is L, and this side is L, and that side is L. Volume is L cubed, right? Length times width times height, but here they're all the same. So the volume of the cube is the length cubed. So that's 4r over the square root of 3 raised to the third power. What's r? (138 picometers). So r equals 138 picometers. What's the volume we need? What's the unit we need for the volume? Cubic centimeters. I think it's easier to convert the radius from picometers to centimeters than to take the volume from cubic picometers to cubic centimeters. So I'm going to convert this right away. Picometers on the bottom, meters on top, centimeters on top, meters on the bottom. I've got two units. They both have metric prefixes, so I should do this in 2 steps. Anybody remember what pico means? 10 to the negative 12. Nano is -9. Pico is the next one, and they're going by factors of 3. Yeah. So pico is 10 to the minus 12. Centi is 10 to the minus 2. So I'm going to be lazy and do that on my calculator. (1.38 times 10 to the minus 8). That's the radius in centimeters. Everybody okay with that? I'm going to take this value and put it in for r in this equation. So I've got 4 times 1.38 times 10 to the minus 8 centimeters divided by the square root of 3, and I'm going to cube that whole thing. Now you need to make sure that you can correctly communicate with your calculator. I'm going to do 4 times 1.38 EE minus 8 divided by the square root of 2. So inside the parentheses, I'm getting 3.90 times 10 to the minus 8th. And then I'm going to cube that. And so I'm ending up with a volume. We're going to go with 3 significant figures here because of the radius. 5.95 times 10 to the minus 23rd cubic centimeters. Anybody else get that? No? I'll give you guys a little time. I may have done it wrong.
I'm missing for R Mexico being 0.000014.
Well, when you do this on your calculator, it can show you the 1 and the 3 rounded up to 4 without putting it in scientific notation. If you force your calculator to show it to you in scientific notation, it'll be 1.38 times 10 to the minus 8.
How would you do that?
You got a 36X Pro?
Yeah.
Okay, so press the mode button at the top and then highlight SCI. And then quit, and then press enter twice. Yeah. Does it show it to you now, 1.38?
Yeah.
Yeah. That's a little idiosyncrasy of calculators. If they can show it to you in decimal form, they will. But sometimes it's rounded off like you wouldn't want. I'm still waiting for confirmation that I got the right answer, but is this a reasonable number? That's a crazy small number, right? But we're talking about a body-centered cubic unit cell. How many atoms are in that cell? 2. Are 2 atoms going to have a really small volume? Yeah. So we should be getting a really small volume. Anybody got that number yet? Or feel very confident about some other number? Okay, I'll calculate it again. I'm going to put in my calculator a different way. That doesn't make any sense. What did I do? So I did it again, and this time I ended up with 1.06 times 10 to the minus 8.
I got 3.26. 3.236.
That's 3.2369.
3.2369 times what?
Times 10 to the negative 23.
Okay. Let me try that again. What the heck did I do? I divided by the square root of 2 is what it looks like. It's the square root of 3. Yeah. I accidentally divided by the square root of 2 instead of the square root of 3. Details don't matter, do they? Yeah, they do. Okay, thanks for catching me on that. So 3.23 rounded would be 3.24 times 10 to the minus 23rd. So 3.24 times 10 to the minus 23rd cubic centimeters. Because if you guys don't catch my mistake, you know what happens? Other people watch my videos on YouTube, and they send me messages. You did this wrong. And I'll look at it, and I'm like, oh, man, I did, and the whole class didn't catch it. But other times, the person just didn't understand, and they're wrong. And that's kind of fun, too. Face-centered cubic. These names are not meant to be confusing. Okay? Here on the face of this, we have the center of an atom. Okay? So we've got an atom centered on this face and on that face, on all faces, right? So this is half of an atom. That's half of an atom. Half, 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 and half. And then a quarter of 8. So we're going to see this has actually got 4 atoms in it. We can calculate, again, the length of the side in terms of the radius of the atom. Here we're using the diagonal along one face because the atoms are touching here. So B is equal to 4R. And we've got this right triangle, so B squared equals L squared plus L squared. We know what B is in terms of R, and so we can solve it. We end up with the length being equal to 2 times the square root of 2 times R. I do not expect you to remember those. If you need it on an exam, I'll give you the length in terms of R. But you do need to know the name of this is face-centered. So here we're talking about the number of atoms in here. We've got half an atom at each of 6 faces, so that's 3 atoms, and then an eighth of an atom at each of the 8 corners, so a total of 4 atoms in the unit cell. Here's looking at it with all of the atoms. It's a bit hard to look at, and this is really kind of hard to look at as well. But the packing coordination number is 12. So this purple sphere on the corner is in direct contact with 12 other atoms. So higher coordination number, higher packing efficiency. So packing efficiency here is 74%. Any questions? There's all kinds of what I think of as fun problems that we can make you do with things like this. Okay, so chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. This requires some critical thinking. I can't show you all the different possible ways to do these problems because it would take too long and you couldn't remember it anyway. You have to be able to think about it and figure it out. So what is density? The mass divided by the volume. Okay, so that's where we start. Density is mass divided by volume. Well, they don't give us a mass, they don't give us a volume. But they tell us body-centered cubic unit cell. So what if we calculate the mass of one unit cell and divide by the volume of one unit cell? How many atoms are in one body-centered cubic unit cell?
4.
2. 4 is the face-centered.
Oh.
Which is what we're thinking because we just talked about that one, but this one's like going back to the previous one, the body-centered. So the unit cell contains 2 atoms. They're chromium atoms. Can we figure out the mass of 2 chromium atoms? Yeah, because on the periodic table, we have the atomic mass. We could do it in atomic mass units, but that's not going to be very useful because we need grams in the end. So 2 atoms of chromium And we need to get this into moles. So we'll multiply by moles, divide by atoms, and then we can use the molar mass, grams per mole. So we find chromium on the periodic table. Where'd you go? There it is, 51.996. 51.996 grams per mole. How many atoms in a mole? 6.022 times 10 to the 23rd. So this is going to be a really small number, but it should be because 2 atoms weigh like almost nothing. So I'm getting 1.72. I'm going to have 4 sig figs here. It's limited by Avogadro's number, actually. 726. There's 4 sig figs. I'm going to write down 2 extras times 10 to the minus 22 grams. Did I do that right? It's a big day for me making mistakes, so just holler if that ends up being wrong. What's the volume? Yeah, we need it into cubic centimeters, right? So we've got picometers here. We kind of did this one earlier, right? I'm just going to start up here. So the volume equals the length cubed. And so that was 4, not pi, 4r over the square root of 3 cubed. Check me, because I'm trying to do this from memory. We've got r being 125 picometers. We want centimeters. So 125 picometers. Picometer on the bottom, what it means on the top, 10 to the minus 12. And then centimeters and 10 to the minus 2 on the bottom. And so we're going to end up with 1.25 times 10 to the minus 8 centimeters. We want to put it in centimeters because our unit needs to be cubic centimeters and it's easier. So the volume is going to equal 4 times 1.25 times 10 to the minus 8 centimeters divided by the square root of 3. Let's see if I can do it correctly this time. 4 times 1.25 EE minus 8 divided by square root of 3. And then raise that to the 3rd power. I'm getting 2.4056.
Yeah, so they have to.
Yeah. 2.4056 times 10 to the minus 23rd cubic centimeters. We calculated the volume of the cell. We calculated the mass of the cell. So we can calculate the density by taking the mass and dividing by the volume. Uh, 1.72686 EE minus, okay, I wrote it down wrong. That's not good. It's 22, not 23. 1.72686 times 10 to the minus 22 divided by 2.4056 times 10 to the minus 23rd. This is going to have 3 significant figures, so 7.18 grams per cubic centimeter. Is that a reasonable density for a metal?
Yeah.
Yeah. Hey Siri, what's the density of chromium?
Chromium is a chemical element with symbol Cr and atomic number 24. It is the first element in group 6. Would you like to hear more?
No, thank you.
Done.
So she showed me the information instead of telling it to me. Wikipedia says it's 7.14. So that's pretty good. Any questions? So another way to think about these crystal structures and how these atoms are put together is to think in terms of layers. So imagine a box and you're putting fruit in the box and you're arranging the layers in different ways, or marbles or ping pong balls or whatever. A simple cubic cell is one where we have the first layer and then the second layer. This atom is directly above the atom below it. And so they're just stacked up vertically like this and horizontally in both directions. So they're just all right on top of each other. This is not how ping pong balls, tennis balls, marbles, anything is naturally going to pack into a box. You can go home and try this. These are actually not going to want to sit up there until you get the whole layer filled. They're going to want to fall into the little divot created below. This is the simple cubic cell, and it has a lot of empty space. We can get more efficient packing just looking at this bottom layer by taking this row and moving it up so that it nestles in this little gap here. So instead of having this one down here where they're all lined up, we're going to take one of these rows and move it up half an atom. And then we'll leave that one alone, move this one up half an atom. We can pack them in closer together that way. Does that make sense? So we're going to do that for layer A. And then layer B, instead of putting it directly on top of layer A, we're going to offset that as well. And so we have A, B, and then A would be directly, the third layer would be directly on top of this one. Can you imagine what's going on here? Visualization is really helpful here. So there's two different ways we can do this. We can take that first layer, the second layer is offset, and then the third layer is directly in line with the first layer. So this is an A, B, A pattern. This is called hexagonal closest packing. It's closest packing because in each of these layers, we don't have a grid of atoms. We've got, well, basically hexagons, right? So this is forming a hexagonal shape instead of a cube. These are going to have a packing efficiency of 74%, a coordination number of 12. So that's similar to the body-centered cubic cell, but it's hexagonal. So if you take that unit cell and cut off the extra stuff, you get this shape. So the top and the bottom are hexagons. And you can do all the geometry and stuff and calculate the length of the sides and stuff. We're not going to worry about it. You're welcome. So the unit cell here is actually just part of that hexagon, because if you take this part right here, that's enough that if you repeat it over and over again, you get the whole thing. But it's called hexagonal because of this thing right here. We can also do what's called a cubic closest packing. So you've got layer A, layer B is offset, but now layer C is offset from layer A. So here the dark red, it would be above these two lighter red instead of like this, where the dark red one is directly above. So if we're looking at the first layer and the third layer, here they are exactly the same. In this cubic closest packing, they are not exactly the same. This one is offset. So this is an ABC pattern. this is identical to face-centered cubic. You're like, I don't see that. I don't expect you to see that. So here's looking at it as in terms of stacking layers. Layer A, layer B, layer C, and then the next layer would repeat. So you put those together, tip it on its side, trim some stuff off, and you end up with the face-centered cubic. So cubic closest and face-centered cubic are the same. Any questions? You ready to run screaming into the, well, it's not nighttime yet, but run screaming into the day? Yeah.